Welcome to the module on machine learning in healthcare, which Holger Kuntz and I have developed as part of the Health-i project. In this module, we're going to explain some of the benefits and challenges of applying machine learning to healthcare data. We're going to take you through some of the basics of machine learning, the terminology that's used in terms of features, feature vectors, and feature spaces, and how these are derived from healthcare sources. I'm going to talk about some of the different ways in which these can be classified using machine learning, and importantly, some of the ways in which these can be evaluated. We're going to deal with three approaches to machine learning. The simplest is something called k-nearest neighbors classification. There's another algorithm which we're going to talk about known as decision trees, and finally we're going to talk about artificial neural nets. I should say at the outset that we're not going to teach you how to program machine learning in a basic programming language. We're not going to show you slide after slide of mathematical formulae that explain the mathematical underpinnings of the different methods we're going to look at. It's very much a practical approach, and it's very much looking at how somebody could use machine learning as part of their portfolio of analytical methods to use in public health research and any other form of data science research. One of the things that I wanted to highlight early on is that we're keen that you should get some experience in applying these algorithms. And so one thing that would be very important for you to do is to look at a repository of publicly available data sets. And we've picked one that we use a lot in our training courses and we think is particularly useful, which is hosted at the University of California, and it's known as the University of California Machine Learning Repository. So one thing that would be really useful for you to do early on is to go to the URL there and have a look at the different data sets that are available and pick some of those to use in the exercises that we'll be suggesting for you in this session and in later sessions. So for this first session at the beginning of the module, what we're going to do is outline the benefits and challenges of applying machine learning to healthcare data and its use in health data science. And we're going to talk you through some of those key bits of terminology I mentioned earlier, this idea of features, feature vectors, and feature spaces. And then we're going to look at how we classify feature spaces and look at how we evaluate different classifications to see which ones are better than others. So I'm sure you've come across the term machine learning. It's been something that's been talked about a lot in the media and in academia and in research in the last 10, 15 years. And it's become a very successful approach to tasks that involve trying to learn a particular rule. So if we're interested in, for example, classifying a set of medical images, so we have one class that contains cancer and one class that doesn't, or if we have a class of patients, one group of whom need to be considered for an intervention, perhaps because they're at risk of being readmitted to hospital, and another class aren't in need of that intervention. Sometimes it's very difficult for us as individuals to identify the differences between these classes, and sometimes it's very difficult to identify a rule that can be used, that can be applied to do that classification. And machine learning is a way of identifying these complex or difficult to identify rules by looking at data, so that they learn from hypotheses. Another reason that we're interested for them in research is that sometimes by applying machine learning to a large and complicated data set, we are able to identify possible subgroups within the data that might be different to other groups, and these can be useful hypotheses that we can use to drive future research. The disadvantages of machine learning is that it needs most applications, most algorithms in machine learning need a lot of labeled data to start with. And the accuracy of the algorithms depends very much on that data. So if your data is not very good, if your data is biased, if there's a lot of errors in your data, then your algorithms won't be very satisfactory. Another problem that people often talk about in the context of machine learning is that it's difficult to identify exactly what the rule is that the algorithm has learned and that the algorithm is applying. So you can get cases where people are reluctant to use machine learning because they feel that they don't quite know what the computer's learned and what it's doing. And we'll talk about some of those issues in later sessions. So this is a slide to help look at the different kinds of machine learning that you might hear about. We're not going to talk about all of these in this module. We don't have much time, and we're going to focus on the methods which we think will be most useful for you. So here you see there are three different algorithms, classes of algorithm that are described: supervised, unsupervised, and then reinforcement. So supervised learning is the kind of learning that we're going to talk about most, and it's called supervised because it uses labeled data in part of the training process. So when the algorithm is being trained, there is somebody who gives it a set of examples for which the outcome is known, and it's then observed whether or not the algorithm is getting that classification right or wrong, and the algorithm is adjusted until the proportion that it's getting right is the highest that can be achieved. Unsupervised learning is different. This is something that we do without initial labels, so in cases where we don't know what the right outcome is. So these are very often used to identify whether a subset of data naturally coheres into 2 or 3 different subsets. And so it could be used, for example, to see if there's a more specific phenotype that we can find within a class of patients with a particular disease, such as diabetes or Alzheimer's. And reinforcement learning is the third class here, and that's very different again. So reinforcement learning is a kind of machine learning that's used not to learn a classification, but to find an optimal solution to a problem involving many different variables. So this has been used in some high-profile experiments, projects recently to play games very successfully. It's become very, very good at playing chess, at playing Go, and other computer games. It's not been applied very much in healthcare, although there are some places in healthcare when you can see what we're doing as being a kind of optimization problem. You could imagine using machine learning. So one might be control of a disease like sepsis, where you're trying to adjust different parameters in order to achieve the optimal control. And there have been some applications of reinforcement learning there. So the first topic I'm going to talk about in detail in this session is that of feature spaces, and this is a really fundamental idea in machine learning, and it's a really important piece of theory, piece of terminology that it's worth getting across right at the very beginning. So let's start with the idea of a feature. So this is a really, really basic fundamental thing. So a feature is essentially the things that we know about the data that we're interested in. So let's imagine that we're interested in patients, and the features are all the different things that we know about the patients. So that might be the age, it might be their diagnosis, it might be their gender, it might be all kinds of things to do with their lifestyle, to do with their genome. Anything that we know about all of the patients in our data set can be a feature that we can use in machine learning. And if we're not dealing with patients, but we're dealing with hospitals, then obviously the features would be different. If we weren't dealing with hospitals, but dealing with, I don't know, some other thing that we might want to apply machine learning to, we would have a different feature set. But it's really, really crucial to get the feature set right if we're going to do successful machine learning. So the features have to be independent of each other. So if you have age as being one feature, and that's an integer that varies between 0 and some number around 100, then we don't want to have another feature which says is this person young or old? And we don't want to have an overlapping feature. So we want to pick features which are independent of each other in order to be have a most efficient description of the space. We also want features that discriminate. So there's no point, for example, us having a feature of nationality if everybody we're interested in is Indonesian, because that isn't going to help us divide up our patients into the different groups that we're interested in. So those are two things to think about, and when we're thinking about what features to use, is are the features independent of each other, and are they discriminating? So just to say a little bit more about the properties of features. So all kinds of data can be features. So we can have categorical features such as male or female or smoker or non-smoker, and we can have numerical features. So we can have age, like I've said, or blood pressure, or any other quantitative variable can be a numerical feature. One of the things that we often do in machine learning is we construct combined features. So an example that you would be familiar of a feature that's created by putting together two other features is body mass index, which, as you'll know, is a constructed feature calculated from the conjunction of somebody's weight and their height. So once you've decided on the set of features that you're going to use to classify your individual, you can think of these as defining a vector in an n-dimensional space. If you don't like mathematical thinking, then that language is maybe going to be a little bit off-putting, but I think it's important to try and get your head around it. So if you know two things about an individual, their height and their weight, you can plot a scatter plot on the x and the y axis. If you know three things, then you could have a visualization which involved an x, a y, and a z axis. But we're interested in trying to classify individuals in spaces that have many, many more than 3 dimensions. Obviously, that's hard to visualize, that's hard to draw, but actually mathematically it's generally no more complicated to deal with conceptually than a 2 or a 3-dimensional space. So if we have genomic data, environmental data, data from biosensors, from someone's social network postings, all of these different bits of information can be a feature. And if we concatenate these, we can get a very, very long, what we call a feature vector, and that feature vector will identify the position of the individual in an n-dimensional space. And this idea of a high-dimensional feature space is really important in machine learning, because what we're trying to do is we're trying to identify regions in this space that have something in common. So if all of the individuals with cancer are in one part of the space and all of the individuals without cancer are in another part of the space, what we're trying to learn is some rule that will divide that space so that the cancer patients can be separated, can be distinguished, can be classified from the non-cancer patients. So here you see an illustration of the ideas here, where you've got a cloud of features that we know about somebody, and we've used those to create a set of feature vectors for each individual, and using those we've plotted the position of each individual in our high-dimensional feature space. And what we're going to do is we're going to try and find a machine learning algorithm which will separate out that high-dimensional feature space so that all of the things which are the same in some sense are classified together. So what we're trying to do in applying machine learning to a high-dimensional feature space is to classify that space, is to partition that space. And in order to do that in the most efficient way, we're trying to find what we call a sparse predictor. So we're looking at the subset of all of the features that we know about, which is the most efficient subset for the classification problem that we're interested in. And one of the challenges in machine learning is that we're trying to work out from a finite subset of the data what the most efficient classification is, and then be able to apply that in the future to some new data that we're going to get. So if we've learned a classification rule from a set of features using our training data, what we want is to be able to apply that rule in the future to a new example and be confident that it will come up with the right solution. So there are a number of steps in doing this. First of all, you have to get the data. We have to find the data. We have to pre-process it. We have to sort out missing data. We have to work out what to do with outliers. There are all kinds of tedious preparatory steps we have to do. And very often what we do next is we try and reduce the number of dimensions in our high dimensional space. And that might involve trying to work out which features are irrelevant or unhelpful. And it might involve trying to identify a set of composite features which we can use instead of a larger set of raw original features. So here's an example of the kind of machine learning tasks that I spend some of my time working on. And so what you see here is a chest X-ray, and this contains this is made up of pixels, and you could think of each pixel as being a feature and feed just the raw image into a machine learning algorithm. Or what you might do is say, okay, we can analyze this using image processing, and we can identify particular features within the chest X-ray, and we're going to feed those into our machine learning algorithm. And that latter approach will be more efficient because we're using a smaller set of features. And this diagram here shows the different kind of features which can be calculated from an image and then fed into some kind of classification algorithm, such as a decision tree or a neural network. This is another example of a machine learning algorithm. This is a support vector machine, which is a kind of classifier which is used to be used more commonly than it is now. And then the features which were used in this example are family history, age, race, ethnicity, weight, height, waist circumference, body mass index, or hypertension. And these are the kind of variables, the kind of features that you might want to look at if you are looking at classifying patients with diabetes or pre-diabetes. So this is just to revisit the material that I've been talking about in order to remind you of the terminology. So this is a data set from the repository at the University of California that I mentioned at the beginning of the lecture. And if you download this, you'll see a range of features which are used in this particular machine learning exercise. There are 768 different instances. Each of those has a number of features, and the last column there, column 9, is the output of the machine learning algorithm. So that's the class. So what we're trying to do in machine learning is we're trying to take a set of features, and we're trying to use those as the input to predict the output. And the output is the classification. And so here the classification will be whether or not the patient had diabetes. So that was an introduction to the thinking around feature spaces, around features and feature vectors and feature spaces, and the classification of feature spaces. I now want to look at the idea that when you're trying to divide up the feature space, what you're trying to do is to find the optimal decision boundary. So if you take one of the data sets that we are going to use later on in the module, the Wisconsin breast cancer data set, one of the things you can look at there is one of the features, if you like, is the radius of the tumor. And you can look at all the different instances in the data set, and some of them are benign tumors and some of them are malignant tumors. So what your task as the machine learning analyst in approaching this data set is to see if you can find a way of classifying the instances on the basis of their feature vectors, so that you can identify the benign cases and the malignant cases, and then you can maybe apply your classification to some new data, and you can predict for somebody whose outcome isn't known whether they're going to have a benign or a malignant tumor. So here we're just looking at a single feature, okay? And what you can see is that the malignant tumors tend to be bigger. They tend to have a wider radius than the benign tumors. The benign tumors tend to be more compact. So just this single feature is clearly going to be of some value in the classification. But it's not perfect, because there is a significant overlap. So we could choose a radius to classify the tumors as benign or malignant. So if we chose a value of 10, for example, then that would correctly identify a proportion of the benign cases as benign, and it wouldn't misclassify many of the malignant cases as benign. But it wouldn't successfully identify a very large proportion of the benign cases. In some use cases, in some applications, that might be satisfactory. We've reliably identified a subset as benign. But generally, we're going to be interested in trying to identify a larger proportion of the population correctly. Similarly, if we were to set a threshold at 20, we would correctly identify a proportion of the malignant cases, but that's of no great value. If you're going to hunt for malignant cases, you need to find all of them. And here you see the value of adding another piece of data. So we've looked at the radius in the previous example. Here we're looking at the radius together with texture. So instead of looking at a histogram, we're looking at a scatter plot. And by looking at the scatter plot, you can see that the addition of this extra variable has improved the segregation of the two categories, the separation of the two categories. There's still some measure of overlap, but if we drew a straight line that optimally divided the benign from the malignant, we'd end up with a fairly reasonable classification. And there are various algorithms that we could use to find that straight line. There are other machine learning algorithms that we can use to find a line which is a better classification than a straight line, which is fitted more optimally to the data. It may be that there's no perfect classifier here. It may be that in order to get a better classification, we need to add more variables, more information, and more complicated algorithms. But however much information we add, it may be that we're not able to perfectly classify the data. That might be just because it's intrinsically not separated, or it might be that the data is noisy, that there are some mislabeled tumors in the data set, and that's what's leading us to think that we haven't been able to classify things perfectly. But what I want you to think about, having looked at these two slides, is this idea that you're looking at a feature space. Okay, so I've only looked at very simple feature spaces, looked at one feature in the last slide and two features in this slide, but I want you to start imagining what it would be like to look at much higher dimensional feature spaces. And what you're trying to do is find the optimal decision boundary within that feature space in order to achieve the best possible classification of the data into the classes that you're interested in, which in this case, in this example, is benign or malignant. And finally, in the last element in this session, I want to look at how we decide whether one of the classifications that we've found is better than another. So I want to look at performance metrics for classifiers. Some of this material will be familiar to those of you with a clinical training from the evaluation of medical tests. So many of you will be familiar with this confusion matrix. If you have a binary classifier and you have a binary classification, you have 4 possible outcomes. If your classifier says that it's a disease case, and it is, it's a true positive. If your classifier says it's a disease-free case, and it is, that's a true negative. If your classifier says that it's a positive case, a disease case, but it's not, then that's a false positive. If your classifier says that it's a disease-free case, a negative case, and it's not, then that's a false negative. And what we're trying to do, obviously, when we're doing classification, is to maximize the number of true positives and true negatives and minimize the number of false negatives and false positives. Sometimes, of course, there's a trade-off to be made. If we're more worried about one class of errors than another, then we can shift the decision boundary for something which is suboptimal in the sense that it's generating more errors, but it's generating fewer of the errors that we care about. So those of you with clinical backgrounds will be very familiar with some of these measures, but there are some terminological differences in the machine learning literature if you compare that to the literature, or the clinical literature around the evaluation of diagnostic tests. So in the machine learning literature, we very often talk about 2 measures, about precision and sensitivity. So precision is the same thing as positive predictive value. It's the number of disease cases which are correctly identified, the true positives, as a proportion of the total number of cases that are identified. So that's the true positives and the false positives. Whereas the sensitivity is the number of disease cases that are correctly identified as a proportion of the total number of disease cases, so as a proportion of the true positives and the false negatives. Both of these metrics are obviously important. Sensitivity tells you how good you are at identifying all the disease cases, and precision tells you how effective you are at identifying those without a large extraneous number of false positives. You can have a simple measure of accuracy, which is the total number that are correctly classified as a proportion of the total. That's perhaps a less useful statistic. You very often in machine learning get people talking about the F1 score, which is the harmonic mean of these 2 different metrics that we're both interested in, precision and sensitivity. And finally, in thinking about the evaluation of classifiers, I want to talk about this really important notion of the receiver operating characteristic. Again, I hope this is familiar to people. It should be part of your clinical training looking at diagnostic tests. But the key idea here is that when you're making a decision about whether or not something should be classified as cancer or not, the threshold that you use is a matter of choice. So if you're very aggressive, you can call everybody back and you'll have very high sensitivity, but you'll have very low specificity. And if you decide to call nobody back, to be very cautious in that way, then you will have very low sensitivity, but on the other hand, in compensation, you have greater specificity. So what you can do is you can plot sensitivity against specificity, or the proportion of true positives against the proportion of false positives, as that threshold is varied. And what you will see is that the proportions will vary. So if you look at the top left of this graph, you'll see a model where there are 2 distributions that differ on some measure, and then a threshold has been applied on that measure, and as a result, some of them are classified as true negative, some of them are classified as true positive, but there's also a proportion of false negatives and false positives because the distributions overlap. But if you move that threshold, you can imagine moving it to the right, and you would see the proportion of false positives decreasing and the proportion of false negatives increasing. So what you imagine is moving that threshold, and as you move it, measuring the proportion of true positives and the proportion of false positives, and plotting those proportions on that graph. And what you'd see is this characteristic curve. If your classifier is completely random, then it would be a straight line from the 0% at the bottom to 100% in the top right. If your classifier is perfect, then it would go vertically upwards from the bottom left to the top left, and then across to the top right. By and large, curves follow a trajectory similar to the one that's illustrated there, somewhere in between. And obviously, the better they get, the greater the area under the curve. If you look at that plot, you will see that the closer the curve gets to the top left, the larger the area under the curve will be. So area under the curve is used as a metric for classification. The bigger the area under the curve, the better the classifier. And this is another slide that makes the same point. So you can see we're plotting sensitivity, or to give it another name, true positive rate, and on the other axis we're plotting false positive rates, or 1- specificity, and a random guess would follow a characteristic curve that was from the bottom left to the top right. Perfect classifier would end up at the top left. And generally, as you move away from the diagonal, if you move below the diagonal, you're getting worse. If you move upwards from the diagonal, you're getting better. The ROC characteristic is a really, really important technique that's used in machine learning classifiers, as it is in the evaluation of diagnostic tests and other studies in healthcare. So that's enough by way of an introduction. I've been talking for about half an hour. So just to remind you what we went through in this session, it began with an introductory an introduction to what machine learning is. Then I went through some terminology that's really important in looking at machine learning and classifiers in terms of features, feature vectors, and feature spaces. And then we looked at a number of different classification methods, or the characteristics of classification methods, and how they're evaluated.